So now we will be talking about how to find the direction of the magnetic field of straight long wire, and this will lead us to the topic of magnetic field lines, and we will see that we can think of magnetic field lines, or we can introduce magnetic field lines, which are virtual lines, just as we did with the electric field lines. But we will see that in contrast to the case of the electric field line, the magnetic field lines are actually lines that do not originate at positive and terminate at negative charge. No, they don't have sources or sinks like the electric fields, but they are continuous lines. So they do not originate at a point and terminate at another point. They are continuous loops. Okay, let's see how we can do this. Now, let's remind ourselves with the formula. This was the magnetic field of a long wire or infinite wire. When I say long or infinite, I mean the same thing here. So, and this tells us that at a distance a from the wire, no matter where are you on the wire, the magnetic field is the same. So wherever, the important thing is how far you are from the wire, okay? Long wire. So this is, what does it say? The magnetic field is the same as far as magnitude is concerned. And so if I take this long wire and I consider a plane here, and I draw a circle of radius r, then at all points on this circle, the magnitude of the magnetic field, as per our formula, is the same. Now what about the direction? On this circle, let's take this point here, for example. Now, r hat, and let's try to find the direction of the magnetic field. Now this is exactly what we have done when we found the magnetic field of a finite wire. We have seen that if you consider a certain ds here and find the magnetic field due to the ds, then this will be the same magnetic field due to all the ds's on the wire. So finding the magnetic field, direction of the magnetic field by this ds at this point is sufficient to tell you what is the direction of the magnetic field. So take a ds here, and since I is pointing this direction, this is pointing up, r hat will be in this direction. It will go from here to here, so it's a vector pointing from ds, which is here, to this direction. Okay, applying the right hand rule from ds to r hat, I mean you just make your right hand fingers point along ds and close towards r hat, then it will be in this direction. So here it will be into the page along b. If you repeat it here, it will be in this direction. It will repeat here in this direction. Here, it's in this direction. The same idea, the same right-hand rule. Try to check that indeed it will give this. So at all points on this circle, the magnetic field here is actually tangent to a circle. And this circle is what? Circle is a circle where the magnetic field is constant. So the magnetic field of a straight line, a straight wire, is that in a plane here is constant on a circle with radius r is the same, and it is tangent to that circle. Now this actually makes us recall what we had in the case of the electric field. In the case of electric field, you remember, we were drawing field lines and we are assigning the rule saying the field line, the direction of the electric field at any point is tangent to that field line. Okay, that's how we used to find it. And that field line was going from positive to negative charge. Here, if we draw a circle, then we say that also at all points here, the magnetic field is tangential to that circle. So this circle is a candidate for magnetic field lines. Okay, look, magnetic field lines is different than the direction of the magnetic field. Okay, so this might be a candidate for a magnetic field line. Okay, because, and if we consider a smaller circle, we will have the same story. Okay, because the field at that circle, smaller circle, will be the same. And again, if you apply the right-hand rule, it will be the magnetic field at each point direction will be tangent to that circle. another larger circle, it doesn't make difference. In all cases, you will have the magnetic field direction will be tangent to that circle. So, but why in this direction, not in the opposite direction? Okay, because of the right-hand rule. So this suggests to us that actually the magnetic field lines are circles that are centered at the wire, and they vary, they spread from that center of the wire, okay, filling the space. And at any circle, the magnetic field is constant. The direction of the field at any point, or the arrow on these magnetic field lines, we need an arrow so that to draw the tangent along that arrow, just as we did in the electric field line, can be given by a right-hand rule. What's this right rule? Right-hand rule is a bit different. It says the following. If you have a long wire, you have a wire, let your right-hand finger, as in the figure here, point along the direction of the current. Then your right hand, the other fingers of your right hand, so the thumb is pointing, sorry, let your thumb point in the direction of the current. Your right hand fingers will curl, rotate, in the direction of the field line. So the arrow that you draw here is the direction in which your right hand fingers curl. Now this gives you the arrows that you need to put on the field lines, okay? Now to draw a tangent, you draw a tangent along that arrow. So if you want to find the magnetic field at this point, draw a tangent here, magnetic field here, draw a tangent here, magnetic field here, draw a tangent here, just as what you did here. So these circles now, which are concentric circles and are centered at the wire, give you the magnetic field lines of the wire. Now, if we want also to assume the same coding rule as we did in the electric field, by saying that the separation, the density of the field lines give you an idea about the strength of the magnetic field there, then we expect that as we go away from the center, from the current, from the wire, the separation between the circles will drop. The separation between the circles will drop, will increase, sorry. It will increase, okay? So the distance between these concentric circles will increase. Why? Because as you go away from the wire, because the magnetic field of the long wire drops as 1 over r, okay, the distance, then it becomes weaker. So you will have the density of these circles as you go away will be smaller. In this case, will be smaller, so they will be less densely packed in this case. Okay, so the separation between them will drop as you go away. So this gives you an idea that the magnetic field is dropping as you go away. To find the direction of the magnetic field, when you know magnetic field lines, you are just find that magnetic field line and draw a tangent to that. Now, of course, this applies to this plane only. But if you take another plane, this is an infinite wire. If you take another plane, you will have exactly the same thing. Okay? So actually, the magnetic field lines are rings that cover the whole length of the wire. It's like bringing rings and stuffing them on top of each other to cover the whole length of the wire. Okay? Now, each of these rings is a magnetic field line. Now, you have actually, if you think of it, you have rings of different radii, and they are just all stuffed along the wire, and their density becomes less as they go away. Okay, so this is the magnetic field lines of an infinite wire. They are concentric circles that go along the whole length of the wire, and these circles have different radii, and their density becomes less and the separation between them becomes less as they go away. So this is how you have to imagine it. Now we can do this by an experiment actually to check that this is the case, or just to give you an idea about the direction of the field of a wire. So if you have this wire here, and you bring compass needles and put them in a circle that is centered at the wire, okay, they will all be pointing in the same direction when there is no current. Now, because of the magnetic field of the Earth. Now, if you have a current passing through them, then you will see that they will be aligned in different directions. Now, what happens is that the field aligns the wire along the direction of the field. Okay, so here the direction of the field is tangent. As you can see here, it's tangent. Here it's tangent, 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 tangent. Because the magnetic field of the wire aligns the needle with it, along it. So this is an evidence that the magnetic field lines of an infinite wire is actually circles, and the magnetic field is tangent at each point, is tangent to that circle. If you carry this plane along the whole wire, you will get the same view. So we have these lines, actually, these lines all over. Again, these are imaginary lines. It's something that we invent. Okay, they do not exist, but they give us a conventional way, a very convenient way, sorry, of imaging the electric field, the magnetic field, graphically, so that we can get an idea about how it goes. If you do a real experiment, this is a photo of a real experiment. If you put iron fillings around a wire and shake it a bit, then you will see that the iron fillings will arrange themselves in also in concentric circles that will reflect the electric field, the magnetic field lines. Probably you have done this experiment somehow, if not with this, probably with real magnets to map the magnetic field lines in your high school. Now we move to consider another example of how to find the magnetic field of some current distribution. We call this a current distribution. That's current flowing in a given conductor of a given shape. We call it current distribution, again using the Biot-Savart law. So in this case, our current distribution is composed of the following. We have a current coming here and then forming an arc, and then the current is leaving. This arc is a part of a circle, and we want to find the magnetic field at the center of that circle. Now, to start with, we immediately say that this part of the current and this part of the current contribute no field here. Okay, so the magnetic field due to this part and this part of the current at the center is 0. And the reason for this, as you know, is because this lies along the direction of flow of the current. So sine theta is 0. Here, sine theta is pi, it's opposite to the direction of the flow of the current, and therefore, as we have said before, we have no field due to these. So the only field is due to this arc, the current flowing along this arc. What is the strategy? Before I do this, what's our strategy? Well, first, our strategy is first to find dB, okay, and then to identify it, find its direction. Then you substitute for the quantities in the formula from the geometry of the figure, and then I didn't look at the symmetry. If there is the symmetry tells you something, cancellations or whatever is that, or tells you that what is the direction of the field all the time, and then you integrate. So we'll start first with the direction of the dB. So we assume that this is the direction of the flow of the current. We have many ds's here. This whole arc is divided into ds's. We show here only one ds. It's in this direction because the current flows in this direction. And this is the r hat, which is the vector that goes, unit vector that goes from ds to r hat. Note that the angle between r hat and ds is pi over 2. And this is the same for all ds's because, you know, this is a tangent and this is a radius. The angle is always pi over 2. Okay? So this is what you have in mind. So what is the direction in this case of the dB due to this ds? It is actually ds is going down, r hat is in this direction, so ds cross r hat, it is into the page. The right hand rule tells me that it is into the page. Okay? And this is the same, this is true for all the dBs due to all DSs here. They all contribute the same dB which is into the page. So I don't need to bother about the direction of the field. Okay? It has only all these contribute a field in a single direction, which is always into the page. So I just need to worry about the magnitude. And I write now the expression for the magnitude. Now, I have here ds only, but in the Biot-Savart load I had modulus of ds cross r hat. But r hat is 1, so it's ds sine theta. But sine theta, theta is the angle between r hat and ds. It's pi over 2. Sine theta pi over 2 is 1. And this is true for all ds's and r hats along the arc, and therefore I end up with only ds. Well, this is quite a simple formula actually, because mu naught over 4 pi is a constant, a square, a is constant for all the ds's. So this tells me that all the ds's here contribute the same dB. Okay, this is what does it tell me. And so this is nice. This is similar somehow probably. Do you remember the ring symmetry that we talked about when we considered the electric field of charge scattered on a ring? It's more or less the same. All of these charges, regardless where they are, they contribute the same potential. Sorry, at that time was a potential. The potential at the ring. Here, this is quite somehow similar, and all the IDSs, or the IDSs that you are along the radius, along the arc, contribute the same field. So now it's I am ready to integrate. If you integrate, well, everything here is constant. Integral over ds. What's the integral over ds? Sum up all the ds's here. Well, what are all the ds's here? It's just this arc length. Well, what is this arc length? It is the angle subtended here, theta, in radians, multiplied by a. Okay? It is s. So you substitute for si theta, and you get this expression. So an arc here, the magnetic field of this arc is, as a magnitude, is always mu naught I over 4 pi a multiplied by theta. Theta here is in radians, not in degrees. Okay, and this is quite a simple expression. So depending upon theta, how large is theta, you get the magnitude of the magnetic field. And the direction is found easily by the right-hand rule. All of them contribute a field in the same direction. And it's perpendicular to the plane defined by the arc. It's either out or in, for example, depending upon the direction of the current. In our case, it was into the page. If the current was flowing the opposite direction, so ds would be always in the opposite direction. In this case, it would be out of the page. Okay? So it's all the same. Now this, of course, tempts us immediately to say, okay, what if this arc was a complete ring? So in this case, what would be the magnetic field? In this case, you just substitute for theta 2 pi, because when you have a complete ring, it's a complete circle, theta becomes 2 pi, and this you get this simple expression. This is the magnitude of the magnetic field of at the center of a ring of radius a carrying a charge, carrying a current I. Okay, and the direction can be found by taking any ds and using the applied hand rule. It's out. The magnetic field is perpendicular to the plane of the ring, but it's either in this direction or in this direction, depending on the direction of the flow of the current, which can be found using the right hand rule easily. Now, a more complicated example. Well, not complicated, I mean in terms of the details, but the principles are the same. In this example, what we have is we have a ring, this ring, but we want to find the magnetic field not at the center of the ring, but at any point along the axis of the ring, as you can see here. So it's a point P, and it's a distance at a distance x from the axis of the ring. The current here is flown in the direction shown, and I want to find the magnetic field here. Now, first of all, I assume that this is divided again into small ds's. Find first, look at the magnetic field dB generated by a given IDS here, and then invoke the symmetry if I can do, and then see how can I proceed. So the first thing is, let me consider this ds, and I want to find the magnetic field here. Now, this is ds, this is r hat. Now again, r hat is a vector goes from ds to the point where I want to find the field. from this. Now this angle is pi over 2, and it's pi over 2 for all ds's here because of the geometry. I mean, this line which goes, which comes from the point on the axis to any tangent to the arc is always pi over 2. This is the geometry. Okay, so this angle between ds and r hat is pi over 2 all the time. Good. So what is the magnetic field dB due to this IDS at this point? Now it will be perpendicular to the plane divided by ds and r hat. So these two together define the plane now. Okay, so you see this dr hat, this ds, they define for you a plane, and it will be, that magnetic field will be perpendicular to the plane. So the plane is in this direction inclined. The magnetic field at point P here will be perpendicular to that plane. Now let's see in what direction. Now ds is in this direction, r hat in this direction, so ds cross r hat, it's up. So it is shown here. So dB is this direction. Now according to this choice of axes, this dB has two components, one of them dP perpendicular and one dB x. dP perpendicular here, I mean the component that is perpendicular to the axis. dBx, the component that is parallel to the axis. Now if this angle is theta, then geometrically this angle also is theta. You can just check doing some trigonometry, and then you can find that dBx here is dB cosine theta, dB perpendicular is dB sine theta. Okay, note that this theta, because this angle is the same for all points on ds, theta also is the same for all points. So this is an important detail. Okay, so anyway, so the x component, or the component along the axis, is dBx. Now we note the symmetry. If you consider now a ds which is a mirror image of this ds across the center of the circle here, it will contribute. You can just repeat what the same argument. You will see that it will contribute a field in this case which is in this direction, and this field will have exactly the same magnitude. The y component, or the vertical component dby, dB perpendicular in this case, will cancel this, and we will have only x component which will add up to this dBx. Now this applies to any ds you can ever choose. Any ds you will choose will contribute a field which will have two components, one component along the x-axis and the other perpendicular to that axis. There is always a mirror image of that ds across O that will contribute a dB where the perpendicular component cancels and cancels. So therefore, when we add up all the ds's, actually we will end up only with a field along the x direction. We don't have field in the direction normal to the axis. So this is, therefore, the meaning of this is that the field now I know of this current that is flowing in this ring at a point P at a distance x along the axis is just along the x-axis. That's the component. And in this particular case, when this is flowing this direction, it is flowing, it is in this direction. Now, what I need to find, therefore, to worry about, therefore, is just dBx. So let me write down what is dBx. I'll start with dB magnitude. This is the magnitude of dB, ds cross r. Now, ds cross r is just ds, because the angle between r hat and ds is pi over 2. Modulus of r hat is 1. So this reduces to ds. This is mu 0 over I, or r pi, the constant, is the same. Now, instead of r square, the geometry tells me that r square is equal a square plus x square. Note that both x square and I square are constant. Okay, they are just the same. Okay, so this is dB. I want to find dBx because this is the quantity that I will worry about. So it is just dBx is just dB cosine theta. Now even cosine theta is constant here. Cosine is the same because theta is the same for all ds's. But we can do more, and note that cosine theta can be expressed in terms of a and x. So cosine this angle theta is just x over r, sorry, a over r, a over r. So this is theta, the cosine is a over r, and r is the square root of this quantity. So you got this. If you substitute this for cosine theta now, then what you need to do is just to and integrate, then so this is cosine theta, and I'm integrating. I am putting here a square, circle or a rectangle to tell you that this is integral over a closed loop. It is just, you know, a convention because I'm integrating over ds over the whole circle. That's the meaning of that. So everything here is constant. Only ds is not the quantity that varies because the x and a's are the same. So take everything out and you integrate. When you want to find bx, you integrate over ds. What is ds? It is the circumference of the ring, which is 2 pi a. And if you substitute this, you get this expression. So this is the magnetic field of a current carrying loop or ring at a distance which has radius a, and it's at the distance x along the axis of that loop. It is again a simple expression, as you can see, depend upon I and also depends upon this geometrical factor, which is a and x. Okay, and it drops as you go away. So as x increases, this drops, as you can see. Okay, so this is the direction, and it is along the x-axis. In this particular example, it is along the positive x-axis. If the current were flowing in the opposite direction, it will definitely be along the negative x-axis, as per the right-hand rule. Now, doing this, having this in mind, we can actually, and remembering what we learned about the magnetic field of magnetic field lines, then we say that from here, we say that along the axis, the magnetic field is pointing always along the axis, always in the x direction. So this is the magnetic field here, magnetic field lines here. So the vector in this case, or the arrow, will be along this direction. Now, think of the ring here. The magnetic field lines of the wire are just concentric circles, as we have seen before. When you have a wire, the magnetic field due to this are concentric circles. And because the current is flowing in this direction, then these circles have arrows in this direction. So you let your right-hand finger point in the direction of the flow of the current in this case, and these circles, which are circulating this current, will have this arrow on them. And this is how I showed this arrow. So you will have this here, and here at the center there will be just straight lines, and then they will start to curve parts of a circle as you go off the circle. Okay. Now these are the magnetic field lines of a real magnet. And you can see that it is very similar. So as if actually a ring is just a sort of similar to a magnetic moment or a real magnet. Okay. So that's what I'm trying to say. Now, we can take a limit of our expression when x is much larger than a. So at very large distances, how does this behave, this magnetic moment behave? And as usual, what you need to do, you consider a over x less than 1, you take it outside, and then if you take this limit, then that's the expression that you get. So the magnetic field in this case along the axis drops as 1 over x cubed. So when you are looking at a ring from a very far distance, you see that its magnetic field drops like 1 over x cubed.